I am talking today about a framework to enable top-down co-design of neuromorphic systems for real-world applications. I just recently moved to the University of Tennessee and rejoined the 10 Lab Neuromorphic Computing Research Group. And so our research group spans the entirety of the neuromorphic computing stack. We are looking at devices, architectures, software, and algorithms and applications as well. And we have researchers all up and down from the computer science side, like me, down to the materials development as well. And we have affiliated faculty at a variety of different institutions. And I put this slide here to emphasize that this work is not mine alone, but actually has been contributed to by most of the people actually you see on the slide. So we're talking about a large scale software framework that have had many hands in it over the course of the last 8 years that we've been developing it. And it is constantly evolving as the field is evolving. So the key challenge that we're really trying to address with our software framework is the disconnect between ongoing research efforts in neuromorphic hardware and the needs of applications and algorithms in the neuromorphic computing space. And the consequence that we've seen with this disconnect is that there has been a bottom-up approach to neuromorphic hardware design, where the hardware is developed first, devices are evaluated, architectures are being developed. And then it gets to a certain point up the stack in a lot of the research, and then it sort of stops. And we saw this, we did this survey paper in 2017, where we looked at neuromorphic hardware papers in the literature up until that point. And we found that only 27% of the papers that had some sort of neuromorphic hardware implementation actually got up to demonstrating even a simple application like exclusive or MNIST. 73% didn't get that far. So why is this important to the community? Well, it's really hard to understand how a neuromorphic implementation can be useful in different applications if you can't see how it's actually performing and what its benefits might be compared to other approaches. So we really wanted to help bridge this gap, develop a software core that would link research going on at the devices, materials, and architectures level with algorithms and applications. And so we began developing the 10 Lab neuromorphic computing software framework. And the core of this framework develops common interfaces to back-end neuromorphic processors. And it also includes a library of input and output coding approaches on how to convert data into spikes if your data is not natively event-driven or spiking, and how to take spiking output coming out of a neuromorphic system and convert it back into whatever you need for your application. We support a variety of different input and output codings, rate, temporal, population encoding, stochastic rate encoding within the framework so that a new user that's coming in doesn't have to build their own encoding approaches. So we link to a variety of different architectures and devices in the neuromorphic community, as well as some simulation frameworks also. So I'm going to dive a little bit more deeply into this. One of the key things that our research group wants to do is architecture assessment for neuromorphic systems, just to understand what are the key features of a high-level architecture design without even thinking about changing the devices and materials that we might want for a particular application. So we do a lot of our architecture evaluation in an FPGA environment. We have two FPGA platforms that we deploy neuromorphic solutions to, Caspian, which was developed at Oak Ridge National Lab, and Dana 2, which was developed at the University of Tennessee. And these also allow us to quickly deploy neuromorphic solutions to off-the-shelf hardware to evaluate on real-world applications to get an idea of what the impact of different architectural decisions would be on the performance in a physical environment. We also link to a variety of simulations of emerging device types. I'll talk more in detail about what we do with these devices and the co-design that we do with them later, but we include implementations, and we've worked with researchers who are doing mixed analog digital neuromorphic systems with memristive devices, biomimetic devices, and superconducting optoelectronic devices as well. We also use our own in-house built simulators. The sort of starting simulation environment that if you're coming in to develop a new application for neuromorphic systems is our reduced instruction spiking processor, or RISP. It's a really stripped down, really fast simulation environment written in C++ that can be used just to evaluate how a sort of very simple neuromorphic implementation might behave on your application. And then we have a generic neuromorphic processor simulation environment, or GNP. This was developed by one of our graduate students who got tired of developing custom simulation environments for every new device and architecture that was being developed and approached for our group. And so this is a flexible processor simulator, also written in C++, with multiple pre-built neuron and synapse models with different devices. And it can be easily extended to support new neuromorphic hardware efforts. So it's meant to be built upon by people who want to come in and use the framework and don't already have a high-level simulation of their architecture. We also integrate with a variety of external simulators. So within our framework, you can use Nest, Brian2, Brian2Gen, which is not actually on here, but we also utilize Gen, BindsNet, Nango, and Nango Loihi. So through the software core, we connect our architectures and devices up to a suite of algorithms, and the algorithms are programmed to that software core instead of being programmed to the underlying hardware. This way, you can easily swap out which hardware you're evaluating on and evaluate different characteristics of your algorithms and how it might perform on these different hardware implementations, which of course have radically different characteristics. So the main algorithm that we have developed within the framework is EONS. This is the algorithm that I've developed. I've presented it at previous NICE conferences. It is an evolutionary optimization-based training approach for neuromorphic systems. It designs the topology and the parameters of the network to address a particular hardware implementation and a particular application. So EONS is often our starting point for evaluating applications and neuromorphic hardware implementations. But within our framework, we also support a variety of other algorithms, including liquid state machines, a supervised STDP training approach, which does not actually require you to have STDP on chip. It will do the weight updates in simulation and then deploy them to the chip. We also support Whetstone, which is a software algorithm that was developed at Sandia National Labs that is a backpropagation-based training approach for binary communication networks that can be deployed to neuromorphic implementations. We support another evolutionary algorithm-based training approach just for training parameters of neuromorphic implementations that's built on a Python library for evolutionary algorithms called LEAP. And we even have support for training decision trees and random forests in scikit-learn and deploying those to backend neuromorphic implementations. So we really wanted to showcase with this particular presentation that you can support a variety of different training and learning approaches, including those that are non-traditional within the framework. So in addition to the training and learning or programmability of neuromorphic systems algorithms that you see on the slide here, we also support within our framework Bayesian hyperparameter optimization. And we use this to determine what the hyperparameters should be of the algorithms and the encoding and decoding approaches that we're using, as well as hardware hyperparameters that can be tuned for a particular application. And so we wrap our entire framework in this Bayesian hyperparameter optimization, as you can see here, and it can tune the hyperparameters for any one of these algorithms or the encoding and decoding approaches. This approach also supports multi-objective optimization to target faster, more energy efficient and or more resilient implementation. So you can include additional objectives beyond just accuracy in designing what your appropriate hyperparameters would be for your algorithms or your hardware or your encoding and decoding approaches. So to enable ease of development for application environments, we also support a set of different types of applications. We support both static and temporal data classification, event and anomaly detection, and control. And so we support the ability to load in your own data sets for static and temporal data, as well as event-based sensing data sets. We're still working on fleshing that out completely, but it's in development. We have an event detection module. We actually have a regression module as well. And we support integration with the OpenAI GEM control environments so that you can evaluate algorithms and neuromorphic hardware implementations on the various OpenAI GEM systems. But we also have in-house developed a variety of our own custom control applications, some of which you can see on this slide here, the different videos. Every single one of these animations that you're seeing was a network that was trained within the 10 Lab neuromorphic software framework for one or more neuromorphic backends that we support. And you can see how it's evaluating and playing the game in each of those different scenarios. In addition to all of our different applications that we support, within our software framework, we also include a network visualization tool that one of our students has developed that allows you to watch in real time how the network is actually performing for a particular task. So if you have a small enough network that you can actually maybe understand what's going on, you can watch the animations, you can build your own network in this tool as well, connect up the neurons however you would like to, and then integrate them within the application environments to evaluate how they're going to perform. So we've used this tool in the past, and we've actually at previous NICE conferences demoed some of our different applications and our visualization tools to help understand how the spiking neural network that was trained for the application is actually solving the application or performing the task. So that's a sort of background on our framework, but I wanted to tell you a little bit more about the neuromorphic research that these tools have enabled. So our goal was really to allow the neuromorphic community to be able to do research at any level in the neuromorphic computing stack and sort of be able to plug and play different neuromorphic hardware implementations, different algorithms, and different applications easily to be able to understand how these things work together. And so one of the key things that we've done with this framework is top-down co-design, where we are working with people who are developing neuromorphic hardware implementations, usually with some sort of emerging device or material, to help them understand what the impact of the decisions that they're making at the hardware level have on real application performance. And so one of those examples is working within our 10 lab group here at the University of Tennessee with Garrett Rose's team, where they're developing memristive mixed analog digital neuromorphic systems. In this case, and in all of these co-design cases, we're using the EONS training approach, but you can swap out the different training approaches as well. But in these cases, we used EONS for co-design to help understand what the neuron and synapse structures should be to work with the memristive-based systems, what plasticity mechanisms would be most effectively useful in different applications, and what connectivity requirements are actually needed for the applications of interest for this chip. And we're using that, designing it in simulation with models of the device behavior to understand what the real performance implications would be of these decisions on applications. And we're using that to inform the design of fabricated systems. And we are currently fabricating the second version of our memristive implementation, the Ravens chip at SUNY Polytech in Albany. Another top-down co-design effort that we've done is with some researchers at Oak Ridge National Labs Center for Nanophase Material Science. In this case, they built a synapse model that is an alomethicin-doped biomembrane. So the synapse is literally the membrane between two water droplets that are encased in lipids. And by applying a voltage to one side of one of the droplets, it opens ion channels in the membrane, and it functions like a chemical synapse. Now, this is a very, very strange device, especially for me as a computer scientist to wrap my head around trying to use, and understanding how to leverage the inherent characteristics of the device and how to design the hardware to suit the applications that we're interested in that would surround this device, the neuron models, for example, was a challenge. And so we used this framework. We developed a simulation of the device based on the experimental behavior of the system. And then we used that within the framework to understand how different design choices would influence performance on different applications with this particular device type. A third co-design project that I wanted to mention was a collaboration with researchers at NIST led by Sonia Buckley. In this case, they came to us to utilize the 10 lab framework to try to understand how to design the neuron and synapse models that they were building out of superconducting optoelectronics and magnetic Josephson junctions. So not only did they want to figure out how to build small networks of these devices to solve particular applications that they could fabricate in their lab, but they also really wanted to understand what the right way to build the neuron and the synapse would be to give them the best performance on these applications. They wanted to understand how complex the neuron and synapse models needed to be with these particular devices for real-world implementations. And so in every one of these cases, you can interchange the application that you are leveraging. We've done control tasks, classification tasks, anomaly detection tasks with all of these because we can easily swap those out within the framework once we've plugged the simulation of the devices into the broader system. The framework also allows us to do algorithmic comparison across not only different algorithms, as you can see in this slide. This was a paper from IJCNN from last year, where we compared EONs with reservoir computing, whetstone, and decision tree training approaches. We compared them across not only different data sets, but also different neuromorphic implementations that had different characteristics. And so we're able to understand what the impact of the algorithms are, changing the algorithm across the hardware as well as the data sets to understand their relative strengths and weaknesses. And we can assess it in terms of things like training time, the network sizes that result, as well as the training and testing accuracy. And in this case, we use that hyperparameter optimization approach to tune the hyperparameters of each of these algorithms independently for the data set and for the underlying architecture. So it could change and give you the optimal performance for that algorithm, tuning the particular parameters so that it would perform best on that combination of data set and hardware. And this is an ongoing study, but is a result from a couple of years ago. We can also use the framework to understand the impact of input encoding approaches across a variety of different applications and neuromorphic hardware systems and simulators. And so we are continuing to study encoding and decoding with these approaches. We're comparing it across algorithms, across hardware, across applications to try to understand, are there rules of thumb that we can use as a community for the best ways to encode data into spikes, and what is the impact of these different encoding and decoding approaches, not only on application performance, but also on energy efficiency and network sizes that are resulting from using these different approaches. So I wanted to end by telling you how we've used this framework on a couple of real world applications. And so one of our big goals in our research group is to connect neuromorphic computing, deploy them into real world applications so we have these drivers for hardware design of the future. We know what the application requirements are. We know how we can use those to inform what the future of neuromorphic systems should actually look like. So the first application that I'm going to highlight is a collaboration with researchers at the National Transportation Research Center at Oak Ridge National Lab. They came to us with a problem where they were interested in using a neuromorphic solution to control the amount of fuel that's injected into an internal combustion engine in real time. Now, there's a lot of research that's gone into engine control units to try to make them run more optimally. These particular researchers wanted to try to minimize the amount of fuel that's injected into the engine to keep it running normally. But what happens is as you start to decrease the amount of fuel that you're injecting, you get to run closer and closer to the edge of chaos, to the point where you start to cause misfires and partial burns in the operation of the engine, which is undesirable. So they wanted a real-time dynamic controller to be able to change the fuel amounts based on the data that they were seeing from the engine. And they felt that a neuromorphic solution would be applicable to this task. So they had a simulation of their engine, and we were able to relatively easily plug that simulation of their engine into our software framework as part of our control environment. And we used EONs in the software framework to train networks in simulation to deploy to one of our FPGA-based solutions. And what we found in simulation is that we were able to see comparable performance to in terms of the number of misfires and partial burns that it would cause with fixed control strategies, but we could decrease the amount of fuel that was required. Now, of course, we evaluated that in simulation, and simulation is not perfect. So we wanted to actually understand what it would look like in the real world. Now, I will pause here and say, this entire research project took place during the pandemic from around April 2020 until we're continuing it on now. But when we first evaluated this, it was September 2020. And so we were all physically isolated from each other. And so we deployed one of the spiking neural network solutions to the physical FPGA board, which our engineer drove to the transportation researchers, handed it to them in the parking lot of the National Transportation Research Lab, and then they had to take it inside and make it work on the engine. We're very proud that they were actually able to do that relatively easily. And this is the video that they took to show us how it was performing. So this is a demonstration of where we were able to take our software framework, plug in a simulation that a domain scientist had developed, train a network for it, deploy it to an FPGA-based hardware implementation, and evaluate it on this real-world application. So the yellow board you see here was the original breadboarded FPGA neuromorphic solution. Is plugged into a microcontroller that's actually doing the spike encoding and interfacing with the host machine that's receiving data in real time from the engine. And at each cycle of the engine, the neuromorphic implementation is sending back a fuel amount to the engine to inject. And what we found was, as expected, not every one of the networks that we trained that got good performance in simulation performed as well on the physical engine, but some of them did. Some of them actually did outperform the fixed control strategies on the physical engine as well. We used that first implementation to improve upon the simulation of the engine that we could use for further training. And we are continuing this project. In fact, today, I believe they're continually evaluating neuromorphic solutions at the engine lab about 30 miles from here. So I'm excited to hear what those results will be. But being able to see how a neuromorphic solution could actually be taken from the simulated environment to the physical demonstration is really important for us, because we can use the information that we've received from those domain researchers on what their application needs are for this particular implementation in terms of size of the system, the power efficiency that would be required, the timing that it needs to be required for these implementations to drive the design of future hardware implementations. And so the final application that I'm going to highlight is our autonomous racing example. In this case, we wanted to evaluate neuromorphic solutions to driving a small 1/10 scale Formula One race car. This platform is not one that we've developed. There's an entire community of researchers who have developed various tools for this. And one of the tools that they have is a simulation environment that in fact is compatible with OpenAI Gym. So once again, we could relatively easily incorporate in the simulation environment as part of our control environment within the 10 lab framework and start training spiking neural networks that could be deployed to a physical car to actually drive in the simulated environment. And as you can see on the slide here, that hopefully you can see the car. There's a tiny little black dot that's driving around the track there. This was one that was trained using the EONS training framework. But we also wanted to understand how different training approaches would perform on this task. So unlike the engine example, where we don't have like a good solution to train from, we wanted to come up with entirely new policies using evolution. With the racing example, we could actually use imitation learning, where we have a driver, an agent that's following the race line that we can use to collect data that could then be used to do imitation learning performance. So with this particular application, we evaluated different algorithmic approaches for this task, both evolutionary approaches and imitation learning based approaches, to see how those would change performance in the simulated environment. There's more detail on this on the journal paper at the bottom of the slide. But because we have the hardware, we can also physically deploy to have the neuromorphic solution actually driving on the car. So because I'm running out of time, I will quickly wrap up. It can be difficult to get started in performing neuromorphic research at any level of the compute stack, and much of the research is done from the bottom up. We've developed this software framework to allow for top-down and omnidirectional co-design, and we've applied it to do research at various levels of the compute stack, as well as to deploy on real-world applications. We love to collaborate. If you are interested in collaborating with us, please reach out. It's not currently open source. It is under constant and active development as we incorporate new algorithms, applications, and hardware into our system. But if you are interested in collaborating, we are open to sharing with collaborators. Also, quick plug, we are looking for postdocs and graduate students for our group, so please reach out if you're interested in collaborating with us. With that, I will thank my collaborators and our funding agencies. One last promotion. I am the program co-chair of ICONS with Malika Payband. We are currently, our call for papers is currently out. The deadline for submissions is going to be extended to April 30th, so please consider submitting. We will, fingers crossed, be having a hybrid event with an in-person component in Knoxville, Tennessee in July. So please consider submitting. Thank you very much for your attention, and I'm happy to take questions.